Okay, for this time. All right. So just a quick reminder, we do have the task 1 expected deadline due tomorrow morning. So if you're not aware of that or what, just a quick reminder. Hopefully everybody can meet this deadline. It was supposed to be Wednesday. I moved it back, so hopefully everybody's able to get it. Everybody will have lab by then, get IntelliJ set up, all that good stuff. And then the deadline for task 1 is next Wednesday morning. So if you, for whatever reason, missed that expected deadline, make sure you're hitting that actual deadline. You don't want to burn one of those recovery opportunities this early in the semester. Task 1 is meant to be just a soft introduction to Scala and just getting IntelliJ set up, being able to submit to Autolab, and making sure the whole process runs smooth. Don't waste a recovery opportunity on this one. You might want those for later in the semester when things get a bit thicker. Okay, so with that, talk about unit testing. Right. So unit testing, this is where I think 116 really starts. This is the first 116 specific topic. I gotta get chat open. This is the first 116 specific topic that we get to learn about. So far this semester has been just learning 115 topics and concepts, but in Scala. We're done with Scala syntax. We're done with introducing language, and now it's our first 116 concept, unit testing. So let's do this. This is where 116 itself starts, in my opinion. This is the first day of 116 lecture. So let's talk about testing our code. So this is a big question that we have, especially out in industry, of how do you know that your code is correct? How do you know if your code's doing what it's supposed to do? You get a spec sheet from a customer. Well, hopefully you get a spec sheet. A lot of times you don't. But you have the software that you need to code up. You code it, you sit at your laptop or your desktop, and you code it all up, and you think it's right, but like, how do you really know it's right? So, and there's kind of this evolution of how to test your code that you go through, at least at UB, because we have Autolab. But you start off to test your code. How do you know it's right? Well, submit to Autolab, click submit on UB Infinite. If the auto grader is happy with it, then it's right? And this is where you should all start out at the beginning of 115. That's really all you have at your disposal at that time. A big problem with this is it doesn't exist outside of academics. Nobody in industry is going to write an auto grader for you to check if your code's right. If they're going to put in that effort, they're just going to write the code themselves. Nobody's going to do all that. If there is any automated testing like this, which is actually what we'll end up talking about, it's going to be written by either you or your team. Like somebody on your team is going to be writing that that solution, that tester. So you really don't have this, professors writing auto graders for you to test your code. Doesn't exist. So we have to wean you off of that as you go through the curriculum. I'll start giving you a little less feedback than 115 did in the Autolab feedback. And then next semester, 220, 250, they'll start giving you even less feedback. I don't know how the current 250 instructors this semester do it, but they usually limit the number of submissions that you have in Autolab. And in 220, they upload a partial grader to Autolab. So it only grade part of your homework, and the rest of your homework, it's up to you to test and make sure that it's doing what it's supposed to do. It's up to you to verify that it's correct. And then after the deadline, they'll upload the full grader and then regrade everything so you get your entire submission graded. But it's up to you to grade at least parts of your submission. Then we slowly start weaning you off of it. In some courses, you won't get any auto grading. When I teach 312, there's no auto grading in that course, for example. Because by the time you graduate, we can't have you dependent on AutoGrader, on Autolab, to find out if your code's right or not. That's not a very effective employee that people want to hire. You have to be able to write code and verify yourself that that code is correct. So recall this code. This is on last Wednesday. This is the first example I give to show you an if statement in Scala. And let's give a problem statement to this. If I were to assign this as a homework task, it would be, or a project task, it would be this method should return large This method takes a double and returns a string. That string should be large if the input double was greater than or equal to 60. It should be small if the input was less than 30. And it should be medium otherwise, if it's in between 30 and 60, inclusive of 30, exclusive of 60. That's how I would write it up, something like that, if I were going to give this as an assignment. So that's what this code is supposed to do. And I claim that this method, this implementation of that method, does in fact do that. It gives me my correct boundaries. It's returning the right string on any input. I'm going to claim that it does what it's supposed to do. But how do we know? Like, how do we actually know? For a code this size, you could probably just trace through this line by line and just reason about it and say, okay, yeah, it is doing what it's supposed to do. Sure, it looks like it is. But how are we going to verify more complex methods when we get there that they are correct? So the next step in the evolution of testing after, when you're beyond just submitting to Autolab is calling your method. Hopefully you've heard this a lot in 115 or AP, whatever prereq you took to get into this course. Hopefully you've at least gotten to this point. I assume that everybody is at this point. You can write a main method, call your method, and then print the results to the screen, run your code, and then verify what's printed out is what is actually supposed to be happening. This is what I did when I first introduced this code. I just had a main method that prints the outputs of 3 inputs to the screen. I run the code, and then I verify that what's printed to the screen is large, medium, small on 3 separate lines. If that's what's printed to the screen, I'm feeling good about it. In 115, hopefully your instructor and TAs push this pretty hard. Whenever I teach 115, I always have to pretty hard. A common case, you go to office hours, your code's not working. You think your code's working. It looks right to you. But whenever you submit, you just don't get any points for it. You get frustrated. You come to office hours for some help. And what the TAs or instructors say is, how do you know this code is correct? Like, did you test it at all? Did you call the method? And then we help you, hopefully, if it's a good office hour experience, they help you write a main method, call your method, because you might say, I don't even know how to call my method. I'm in 115. I've never seen this stuff before. They'll help you call your method, print the value to the screen, and check on certain inputs if your code is doing what it's supposed to do. So that's like the 115 level of testing, at least printing to the screen the output of your method on various inputs. This has its limitations, and especially with this course being about how to write large pieces of software. What happens when we have hundreds of files, thousands of methods, tens of thousands of lines of code, or hundreds of thousands even? In my first internship I went to, I was working on a project, obviously on part of a team, where the code base that I was starting with was 250,000 lines of code. And like you just can't do anything manually when the code is that big. And that's not uncommon. That's realistically a small code base for like professional software. It was a shorter term project. The long term project out there is going to have millions of lines of code. Don't be surprised if you're working on millions of lines of code. A project with millions of lines of code when you get out there. Anyway, you have a project that big, and you want to test it to make sure everything's working the way it's supposed to do and you don't have any bugs for your end users. You run this code and you're just printing outputs to the screen. You run all of this code and you have pages and pages and thousands of lines of stuff being printed to the screen, and you verify manually that everything printed to the screen was what it's supposed to be. Nobody's going to do that. Nobody should ever be doing that. That would be a terrible task to have. So we need to evolve this to the next step, and that's where unit testing is going to come in. And this is where we're going to automate that process. We're going to do effectively the print to the screen and verify, except we're going to get rid of the manual portion of that and automate that. So now we can hit one button, test the entire project, everything about that project, test it in one go. And especially, you might think, well, I don't have to test the whole project. I just have to test the new code that I wrote. But when you have a large project like that, all the pieces of code are, at least at some level, interdependent on each other. So one change over here in the project might break something over here in the project. So you have to retest everything. We're not going to do that manually. We're going to automate it. We automate things. We're computer scientists. We're going to automate anything we can. So with unit testing, we're going to write a series of tests, and then hit one button, run our test suite. And if all of those tests pass, Then we're going to say that the code is good. The code passes our test suite. And if even one single test, maybe you have 1,000 test cases, 1,000 inputs that you're checking the outputs of for a method, and only one of them, that code returns the wrong thing, that code fails. That's incorrect code. We need 100% here. We need every single test case passing, or else the test suite is going to say that code is wrong, this test fails, fix it. And this is really useful in when writing software. Your test suite, your goal of your test suite is to expose bugs. If you have a bug in your code, you want your test suite to find it. So you want to think of every possible bug that your code could have, write tests for all those bugs, and then if you have one of those bugs, you run your test suite, and your test suite's going to help you out and be like, hey, you got this bug, and then fix it. Then it helps your debug cycle. You can't debug any bugs if you don't know the bugs are there. So the test cases are helping us find those bugs, expose the bugs so we can squash them. And here's what that looks like. So here's the syntax. I'll spend the next few slides going through this, this syntax of a test suite. But this is going to be a test suite in Scala. So I am doing the same thing that I was doing with the main method. It's the same three inputs, 70, 50, and 10, except I'm going to automate the checks and make sure that they return what they're supposed to return. This is going to use the Scala test library. This is an external library, which means that it's a library, it's a package, it's code that's not part of Scala. So we have to download this and link it to our project, which used to be a pain, but IntelliJ kind of just does it for us. It's done it on your projects already, you didn't even know it was happening. So when you look at the code, you'll see this pom.xml file in both the examples repo, the example code, and your project one after you clone that. You'll see this pom.xml. The reason for that is to specify all of the dependencies, is what they're called. Dependencies and external libraries are one and the same. All the dependencies are defined in the pom.xml to say, hey, here's all the code that you need that's not part of Scala. And then we run software called Maven, which is going to read the pom.xml, download all those libraries, and add them to your project. Once all that's done, then you can import that code using our import statements and start using those libraries that we downloaded. IntelliJ is really good about when you clone a repo, it'll see that there's a pom.xml and it'll run Maven automatically. But if you do get import errors on Scala test, you want to find and run Maven to be able to download those dependencies. I haven't seen it in a long time where Maven didn't run automatically for a student, so this is mostly in the past. When we first started using pom.xmls, it didn't do it automatically and it was a pain. The first lab had several more sections to it to do this part. But it's very painless now. All right, so let's look through this code and talk about each part of it. First, importing the library. I'm using Scala's wildcard for this. The wildcard is usually a star, an asterisk or a star. It's an asterisk, but we call it a star. In most languages, for whatever reason, Scala decided to use underscore for their wildcard. So what this means is there's a package named org.scalatest. Give me all of the code in that package. That's that wildcard saying. Give me everything. I don't want to specify each individual file. I don't want to specify every single one of them. Just give me everything that's there. Everything you find in that, give it to me. One of the things included in that is fun suite, short for function suite. And we're going to create a new class that extends fun suite. Class and extends, those are learning objective 2 terms. The short, very brief explanation of it before we get into LO2, where we'll spend weeks talking about that stuff. The very short answer is that we're going to create a test suite that is a function suite that's going to be used to test functions, or in our case, methods. This is going to be the name. There's a little bit of vocab here, like reading through my homework docs, a little bit of vocab that you'll notice. The name is going to be the name of the test suite. So when the homework doc says create a test suite named task 1, and that does this stuff. This is the name of the test suite, and that should match the name of the file, and that file should be in the tests package and specify the test package. For project 1, that's all set up for you, so you can use that as an example for the other projects where I don't set it all up for you, because I want you to go get practice going through the process in later projects. Project 1's all set up for you, though, as an example. Then a test suite can have multiple tests. I only have one in this one, but if you want another test, you would do the same, everything that's highlighted, do that again beneath it, and have multiple tests. And then test cases. Oops. Well, I'll jump ahead a little bit. Test cases is each input that you're testing the output of for that method. So the next thing, the syntax for a test. Test is part of fun suite. It's something we get by extending that. Test, using this syntax, give it a string, which is going to be the test name. And I encourage you to put meaningful names here, write actually what that test is testing. But if you don't, I see in office hours and in code and in Autolab, test 1, test 2, test 3. That's fine too. I'm not going to get mad at you or anything. But it will help you when your test suite is failing. You can very quickly see, like if it says test 3 is failing, that doesn't really give you any information. But if it says testing for truncation errors on doubles, for example, that's going to give me a little more information. Just cuts out a step in my debug process. I don't have to look up, wait, what was test 3 again? But if you're not going to do that, I ain't gonna care. That's to help you to give those meaningful names. And then finally, the body of the test. This is any code that you can write. Anything you know about programming, all your tools, if statements, loops, data structures, all that stuff is available to you here. The one thing that we get from FunSuite is this assert method. Whenever you want to check a test case, check a method on a specific input to see if it returned the right output, use this assert method, and this is going to take at least one argument, which is going to be a Boolean expression. And it's a Boolean expression that you expect to be true if the code is doing what it's supposed to do. So here I'm calling my compute size on 70. I expect that to return, I expect this method call to resolve to the string literal large. So I'm going to assert that that's true. I'm going to say this Boolean expression, this equal, should be true. If that is in fact true, this test case passes. That means compute size returned the expected output on the input of 70, and this test case passes. Same with the next two. So I have 3 test cases. I'm going to call it with 50 and expect medium, call it with 10 and expect small. And if all 3 of those test cases pass, then this test suite is going to pass. If any one of these 3 fails, the test suite fails, and the test suite says, hey, you have some work to do on your code. Go fix some code. We have an optional second argument, which is going to be what's printed to the console when the test fails, if the test fails. So if any of these tests fail, in this case I have it set up to print out the input that it failed on. So I just want some information. Hey, if this test case fails, at least tell me the input that it failed on, so I have at least a little bit of a hint as to where to look to start fixing things. So you can use the hint text as much or as little as you want. Again, I encourage you to use it, but it's there to help you and shorten your debug cycle. So if you don't use those and I see you in office hours having a question that could have been solved by nice hint text, I might mention it or something. But it's up to you how much or how little you want to use them. But it does make your life easier. I do recommend using it. But it is optional if you just don't have a second argument. If all that's gone, you still assert the Boolean expression, and things still work just fine. So I'm in the, and I'll start doing this more as we go through the course. I'll constantly jump over to IntelliJ to show a little bit of code. I'm going to be in the examples repo most of the time, so hopefully you all have this cloned. Some of you haven't had lab yet, so unless you looked ahead on the document, you'll have it cloned later today. But I'm in the examples repo that you cloned, and I'm in LO1 program execution, testing, test compute size. So when I go here, I'm going to see that exact code that we just saw in the slides. This test suite is checking for 70, 50, and 10. And to run a test suite, there are several different ways to do it. For my money, I like to right-click on the file and go to Run. That's going to run this test suite and test my code. And if you get this green check mark, that's good. That means everything passed. Your code passed on every test case, every test, the whole test suite passed. You're feeling good. Those green check marks really feel good to see. But if we change our code, so I'm going to go up to the code for this example, and just make a small change. I'm just going to do a capital M for medium, which is incorrect. It's supposed to return medium in all lowercase letters. I don't have anything in my test to ignore case or anything, so this is an incorrect solution. I'll run this again, and this will be the test suite. Oh, oops, I forgot to mention some. So this arrow at the top of the screen, a lot of you probably figured this out by now, but just in case, I want to make sure everybody hears it. The arrow at the top of the screen, in the top bar in IntelliJ, will run the last thing that you ran. So whatever the last file I ran is, that's what it's going to run. Now I know I just right-clicked on test compute size and ran it. So when I click this again, I know it's going to run test compute size. If I want to run something different, I'm going to go right-click the file again to run it again. And when I ran that, the reason, I should explain why I like to right-click on here. If you click, like, say, this arrow right here, it's only going to run this test. And if you have multiple tests, you might think you're running all of them, but not actually running them all. You have to click this one up here. So instead of trying to remember that and always click the right one, I just always right-click the file to make sure I don't make that mistake. So I made that mistake before and lost hours of my life debugging something that didn't exist. It was a pain. I don't like wasting my time, so I'm going to right-click and do the foolproof way of doing it. So this is a test suite that fails. You're going to see these X's. This test suite failed, and if I click on the test name that failed, it's going to give me some good information. The Scala test library is pretty good about giving you a good amount of information most of the time, but it also gives me what I'm printing to the screen, which is the 50. But it's telling me, look, I expected this, you gave me this, and it even highlights the difference. It says, look at the different characters is this lowercase and capital M. So it gives you a lot of information. Once you get used to seeing this format, there's a lot of good information there when it fails in certain ways, of course. So this is a failing test suite, and then we can fix our code, run it again, and get back to passing. Forever. All right, any questions on this? I'm going to hop back to slides, if not. Feeling good about the structure of a test suite? Yes? Mm-hmm. So if you want to see what this method returns, so I'll usually, I like to do something like this. I'll grab this. I'll grab the output and slap it in. Oh, geez, what am I doing? I'll grab the output and put it in a variable. And then I'll give some text for me here. On input, returned. And I'll just throw that in my hint text. So now if this test case fails, it's going to give me that. I might as well break it, actually. Now that's going to be in my hint text. So that's the way you can use the hint text to give yourself a lot more information and more quickly debug these things. And then I get my text right here. On input 70, returned RNG or RGE instead of what I expected. If you have that in your hint text, your debug cycle goes way down. It's a lot quicker to find things. In this case, the library itself was pretty good about showing that. But if it's not set up in a way to do that for your test case, use your hint text. Any other questions? All right, so that's the structure of a test suite. Test suite, the name of the test suite, tests, and then individual test cases. Bless you. Individual test cases. So a little bit of terminology. You'll hear me say, kind of mix those three terms: test suite, test, and test case. I'll be using all three of those often. So my next question, which is a big question, big unanswered question in industry. Everybody has different answers for this. Every team has different answers. Every individual has different answers. But my question for you, but the overall question that everybody has is, how much testing is enough testing? But my question for right now is this enough testing? I'm calling my method on 70, 50, and 10, and making sure that on those three inputs, I'm returning the right outputs. Is this enough testing? Yeah. Yeah, exactly. So I hope everybody says no to this one. This is not enough testing. We want to test the edge cases. We want to check these boundaries and make sure that we're really testing the code. Your goal of writing a test suite is to really put your code through the ringer. Really try to find an input where your code might fail. Think of any possible thing that could go wrong and write a test case for every single thing that you think of. Write tons of test cases, lots and lots of tests. There's no such thing as too many tests. Well, maybe. So here's a correct solution for this code. This is for this problem. This is the code we've been seeing. Of course, in programming, there are always many, many different ways to approach a problem, but this is a correct solution. This is one way of implementing this method that is correct. It does the correct thing. We run the test suite on this. Test suite says, you're good. Cool. Here's an incorrect solution. I'm changing the boundaries to 65 and 20 instead of 60 and 30. This code is wrong. It doesn't do what it's supposed to do. But it passes my test. It's right on those three inputs that I checked. So my test suite is going to look at this code and say, that code's good. But we know that code's wrong. This is a flaw in my test suite. My test suite isn't thorough enough. I don't have enough testing. Because there are many, we can change these boundaries quite a few times. There are a lot of implementations that are wrong that my test suite is going to be like, yeah, that's good. And that's a problem. That means my test suite is not good enough. Let's tighten it up a bit. Let's get right up on those boundaries and check these boundaries a bit tighter. I'm going to check right on either side of each boundary. I only felt like typing 2 9s, but you could type up more 9s if you want to get closer to them boundaries. And run this test suite. It's certainly going to fail that incorrect solution that we just saw. But my question again is this enough testing? Yeah. No. We have a no. Yes. I'm fine with that answer. This one's a little more debatable. For my money, I would like more testing. But there is a reasonable argument to be made that this is enough. I would argue against that, and then at the end of the argument, I'd say, in the time that we argued, you could have just wrote more test cases. would be my debate, how I would have that debate. But there is an argument to be had there. You're checking the boundaries. As long as somebody codes this up as two boundaries, then this is going to check if that's correct. Maybe you want to write more 9s out there to get closer to the boundaries. But if you have two boundaries, it's going to check those two boundaries. Problem is, what if somebody coded it in a way that doesn't use two boundaries? What if they said, if input equals 60, return large, else do some boundary checking? That's going to pass this test suite, but be clearly wrong. So I would like more testing. But there is a debate to be had. Let's crank it up a little and add a lot more test cases. Once we get enough test cases, I'm not going to hard code all the asserts. I'm not going to have one assert line for each test case. So we get a good excuse to use some lists and reinforce how lists work in Scala and how we can use data structures in our test cases. So for this, I'm going to create 3 lists. A list with all the inputs that I expect the output to be large, a list with all the inputs where I expect the output to be medium, and a list of all the inputs where I expect the output to be small. And just as a reminder, this is how we add. I'm appending an element to a list. We use this : plus to append to the end, and always reassign to your variable to actually have that change take effect. And then I'm going to use some loops. I'm going to loop over each data structure and get what I expect the output to be, check what I expect the output to be. And my hint text is a little more important here. I have more test cases. If my code fails, I want to know exactly which test case failed. So I want to make sure that I'm printing those to the screen in this case. Then is this enough testing? Oh, and in the real world, we would want to have a talk with our clients and figure out what behavior they want with negative numbers. I'm going to say negative numbers are less than 30, so they're small. So that's how I'm coding my test case. In reality, before you code the test case, because the test case, in a very real sense, is going to define the expected behavior, you would want to talk that out with your whole team, your clients, make sure that you get what they actually expect for negative numbers in a case like this. I'm just saying less than 30, so small. Is this enough testing? I'm happy with this test suite. I would stop here. Maybe if I think of a few more, 90 to 1,000 is a pretty big gap. I might want to put like 500 in there or something. But this is more reasonable. This I'd be more comfortable with as a test suite. But this is a question that every developer, every team is going to have a different answer for. When do you stop testing? For this semester, it's obvious. It's when Autolab's happy. If Autolab coughs up points, you're done testing. I just want to introduce unit testing to you, so by next semester, hopefully you have a better answer for yourself other than when Autolab's happy. But for this semester, it's when Autolab's happy. But out there in industry, when do you stop? When do you stop writing tests? It's a big question. It's a big open question. You can, just for this method alone, you could write test cases for the rest of your life and still not have a completely finished test suite. You would want to test every possible double if you want complete testing, 2 to the 64 inputs, and then once you finally type all that up, just running that test suite would take longer than the rest of your life. That's 2 to the 64 is a ridiculously large number. You're not going to fully test anything. So you just have to decide when to stop, and it's whenever you're comfortable that passing that test suite gives you reasonable assurance that that code is actually correct. That unless something really strange happens, incorrect code isn't going to pass the test suite. But it's a big question. It's a tough question to answer. All right, we talked about doubles on last Friday. They're coming back in a big way when we're talking about testing. So how do we test doubles? How do we test, specifically, how do we test a method that returns a double? How do we test if it's correct? When we know that we have truncation errors with doubles, we can only we have to fit our floating point values into 64 bits. There has to be some truncation for most numbers. We're not going to represent values exactly in memory. So how are we going to test methods that return doubles with this in mind? like for task 2, you're writing a method, you're writing tests for a method that returns a double. So right from task 2, we have to start thinking about this, of course, by design. So with truncation errors, in most cases, it's not going to make that big of a difference if you're just using a method, a value for math. For example, this code that we saw, this C isn't going to be 0.3 exactly. It's going to be 0.3 with a whole bunch of zeros and then a 4 trailing at the end. But if we're just using that for math, we're going to be close enough. We're going to be fine with that. The problem comes in if we're writing a test suite that's going to test doubles, and we do something like this. 0.3 and what's stored in C are practically the same, but they are not equal to each other. So when we say assert that those doubles are equal to each other, that test case fails. Even though the code is doing what we expect it to do, it's close enough, it's fine. Depending on the application, I suppose. But this test case is going to fail. So we have to think about how we're going to test doubles. How are we going to compare doubles? And the answer is never going to be equal, equal. We're not using equal, equal to compare doubles. Instead, what we'll do is say, are these two doubles close enough within some tolerance that we're going to choose? So I'm going to choose some tolerance, 1/1000th in this case. And I'm going to call this epsilon. I borrowed this from math. Whenever you have a really small value in math, you call it epsilon. I'm going to do that same thing. I just stole that from math. But I'm going to set my epsilon, and I'm going to say, as long as these values are within that tolerance of epsilon of each other, I'm going to call it good. So to do this check, I'm going to subtract the values. Here I'm taking C minus 0.3. The problem with this subtraction, so I want to get the difference between these two values. The problem with this subtraction is if C is slightly less than 0.3, it's going to be a negative value, which is going to mess up all my logic. So I'm going to take the absolute value of that difference. Now whether I have C minus 0.3 or 0.3 minus C, doesn't matter the order. I'm going to take the absolute value, and that's going to give me the magnitude of the difference between these two values. And I'm going to check if that difference is less than my tolerance. If it is, I'm going to pass that. I'm going to say that test case passes. Because these two values, these two doubles are close enough. They're within my tolerance of each other. And I'm going to make sure that my tolerance is large enough that it's going to wipe out any truncation errors. So that 0.00004, that's way less than my 0.001. So it's not going to matter in this computation. And my test case is going to pass. It's going to ignore those truncation errors and pass this test case. The choice of epsilon is pretty important. You have to think of what epsilon makes sense for your application. For example, task 2, you're computing the average population of a country. I'd say if you're within 1/1000th of the actual average population, I think we can all call that good. Like 1/1000th of a person off that we're going to allow, that's fine. If you're doing the application objective and you're checking distances between cities, if you're testing your greater circle distance method, and you're talking about kilometers on Earth, maybe you could be off by an entire kilometer and still call that good. If you're testing the distance between atoms, maybe you want a significantly smaller epsilon. But it's up to your specific application what epsilon makes sense for that application. Never use equal, equal testing doubles. Ever, ever, ever. Don't do it. Don't do it. It's not going to work. Autolab's going to be mad. You won't get points. Don't do it. And beyond college, you'll break stuff. You'll have broken code. You'll have bugs in your code. Don't do it. All right, so testing in CSE 116, there is a Piazza post on reading the Autolab feedback, which explains some of this, but I want to make sure I cover it in lecture as well, of what happens when you submit code. So with task 1, the test suite is given for you. You go in the test package. There's a task 1 test suite. You run that. You can run that. It'll test your code. So for task 1, as you're writing your code, run that test suite. If that test suite passes, you can confidently submit to Autolab, and Autolab should be giving you points. From task 2 onward, you have to write your own test suite. So in Autolab, I'm testing your code, but I'm also testing your test. And I want to explain how testing your tests is working. So when you make a submission, your test suite is ran against 3 different categories. One, it's going to be ran against your code. This should almost always pass, because you should be running your test suite against your own code. In IntelliJ, you submit to Autolab, it's going to run the same code against the same code, the same thing that you did in IntelliJ, and it should pass. There's a rare case where this doesn't pass. It's when a student will modify the cities.csv file and pass locally, but then when they submit to Autolab, well, I have the original cities.csv in Autolab, and then it's going to be a different test because I'm using different data. This is most common when students like to delete the header line in cities.csv because it's too much of a pain to work with, so let's just delete it. Well, that header line exists in Autolab. So that's one case where this might fail. Other than that, this should always pass. I shouldn't see any feedback in Autolab where your test suite doesn't pass your own code, because why are you submitting? You know you have work to do. Then it's going to be ran against a correct solution. So there's a correct code that always returns the correct answer in Autolab. Your test suite is going to be ran against that, and your test suite should always pass the correct solution. If you're not passing the correct solution, you got to work on your test cases. That means you either coded a test case that doesn't fit the homework description of what that task is supposed to do. You're testing something that isn't what that method is, the actual output of that method is supposed to be. Or you're not allowing tolerance in your doubles. So my correct solution for task 2 is coded in a way that I get truncation errors that are strange, I guess, that are different than the truncation errors that you'll get when you're testing your own code. So if you're testing doubles with equal, you're going to fail the correct solution on task 2. Then finally, a variety of incorrect solutions, which is where students spend most of their time trying to get these incorrect solutions. So your test suite is also going to be ran against intentionally incorrect solutions, and your test suite should fail each one of them. You should have at least one test case that's going to expose each one of those incorrect solutions. So it correctly marks them as incorrect solutions. If you get all those, then your test suite passes my scrutiny here, and Autolab's like, okay, your test suite's good. And if your code's good, you get credit. So just to show you, I usually won't show these, but for task 1, I just want to show you an example of what's actually going on in Autolab, because I do get a lot of questions on this. Is my incorrect solutions for task 1, I have them coded in Autolab as though you were writing the test suite, so you can get used to seeing the feedback. The incorrect solutions for task 1 are these ones. Usually you're only going to see my cryptic names for these on the left. You won't actually get to see the code, but just to show you an example of what these actually are, I want to show you the code once. So always returns empty string, does what the name implies. It's an incorrect solution that just strictly returns empty string. This is the freebie. I usually have at least one incorrect solution like this that's just so obviously incorrect. It's just checking, did you write any test cases at all? This will only pass on country names that aren't in the data, because you're supposed to return empty string on those ones. That's the only time this one will be correct. So if you have any test case that has any actual expected output that's not empty string, you're correctly failing this one, which is what you should do. Requires matching case isn't checking the case of the country name. So I get this country name that I have to look up in the file. I'm going to read the name of the country from the file, and I'm just going to check if they're equal. I'm not calling 2 lowercase like I should. So capitalization will matter for this incorrect solution. So this is saying, do you have at least one test case that messes up the capitalization of the input country name? And then returns uppercase country code, doesn't call 2 lowercase on the country code. So are you making sure that the capitalization matters on the returned country code? For example, if your test suite calls 2 lowercase on the returned value, you wouldn't expose this incorrect solution. So these are the incorrect solutions for task 1. If you combine these last 2 incorrect solutions, you might be able to come up with a correct solution. There's no reason for any of you to miss the deadline tomorrow morning. I'm giving you everything you need to be able to get this. There's no reason. Get that first expected deadline. Hopefully you all have IntelliJ set up. If you haven't had lab, if you have lab later today, make sure it's set up then. write your code and get that task 1 done. I want to see everybody getting that expected deadline. So with this incorrect solution that's not checking for the capitalization of the country name, the first test that I have in the test suite that I give you isn't going to expose this incorrect solution. So if all you had was this for testing, where all the capitalization of the inputs is proper, you're not going to expose that solution, and you're going to pass an incorrect solution and get a frowny face in Autolab. So of course, we added more tests to make sure that we get rid of that incorrect solution. So when you're writing test cases, things to keep in mind. Include common cases. These are like the regular inputs that I have here. Include uncommon cases. When somebody has really strange capitalization, we still want to make sure that that code is correct and is going to handle that. Include edge cases, which are the really strange inputs, the ones that don't really match any common cases or uncommon cases that somebody would actually use the method for in general. Empty string, empty data structures, these are always good edge cases to test. And finally, write lots of them. You can't have too much testing. Oh shit, I didn't realize we have only 1 minute here. But I wanted to get through that last part because obviously it's the lecture question. I had to get through that last slide. And with that, have a great weekend.